Harnessing and controlling the spin of electrons is the goal of quantum computing. Where a conventional computer bit is either 1 or 0, the quantum bit, based on the spin of an electron as it orbits an atom, is a combination of a 1 state and 0 state at the same time. This quantum bit, or qubit, opens a whole new era of programming and promises to solve problems that conventional computers can't. But to be effective, you need many qubits, and you have to be able to control the spin of each one.
And I guess one of the critical problems that we have is these qubits are very, very close together. So we've got a beautiful atomic system, but they're, literally tens of nanometers apart. And so how do you address one without affecting all of them at the same time? And any kind of, electrode that you put down is going to affect all of them in the same kind of electric field or magnetic field. And so that's really the critical part of this paper. How do we individually address those individual electron spins on these atoms that are so close together?
But now a team at the University of New South Wales in Sydney has published a paper in Nature Communications magazine showing that if the electron is bound to a different number of phosphorus atoms than its neighbouring electron, each will respond separately to tuned electromagnetic fields.
The beauty about phosphorus clusters is that a single electron bound to one of these clusters will have a different rotation frequency. So now you can choose the right frequency to only rotate the electron spin which is bound to the phosphorus cluster, but at the same time you do not rotate the electron spin which is hosted by the single phosphorus donor. And vice versa. You can also choose the frequency to rotate the electron spin which is bound to the single phosphorus atom, and you do not rotate the electron spin which is hosted by the phosphorus cluster.
Importantly, the UNSW team, in collaboration with Sandia National Laboratories, has shown that the electron spin is not degraded by the presence of multiple phosphorus atoms.
And that we did by realizing this device in our laboratories. And it is such a cluster of about 4 phosphorus donors. And next to it, we fabricated a readout architecture. And with this readout architecture, we were able to measure the lifetime of the spin qubit. And we found the lifetime of the spin qubit is still very long compared to that of a single donor.
So this is a really unique and nice method about how to address individual qubits. And I think when you go to long-term quantum computing, it's the kind of thing that we're going to really have to understand how to do well.